Hi and hello everyone. After having seen the basics of queues and some general results and having acquired the background from the theory of stochastic processes that is needed to understand and analyze a queuing system through a Markov chain model, we will now move into the analysis of queuing systems of various different models which can model different queuing systems. Okay. The first step in the analysis is to consider queuing systems which are broadly called as birth death queuing systems or elementary queuing systems or exponential model based exponential distribution based queuing systems, the simplest one. Okay. Many simple but interesting and non-trivial queuing systems can be studied through birth death processes. Okay. And it's so simple and yet it's highly effective in implementing many of the real life situations which can be modeled through this birth death processes. Okay. Recall that a BDP, we will again revise little bit more about this BDP, but now BDP we know that is a continuous time Markov chain on the state space of non-negative integers where transitions occurs only to the neighboring states. So, from a queuing perspective, this would mean an arrival is regarded as birth in the context of a birth death process and a departure is regarded as a death and with the state denoting the number in the system. Whenever we are talking about solution of analysis of a queuing system, we primarily mean the number in the system. So, that will be our main objective or main object of study in any queuing system, that our queuing system, whether it is single or network or anything, that is with the primary objective will be there. Okay. So, that is why the state mainly denoting the number in the system. Since it is a birth death, we know that the transitions can occur only one at a time. So, that means the arrivals and departures happen one at a time, and since the time is continuous, so the probability of an arrival and departure happening at exactly at the same time is 0 or negligible, right. So, we can always slot it in such a way that they are distinct. We will always assume, unless stated otherwise, that the arrivals occur from an infinite source for all queuing systems, whether it is birth death queuing systems or otherwise. When we will go later on into more general Markovian queuing system or semi-Markovian queuing systems, we will always assume that the arrivals occur from an infinite source, which means that there could be there is a infinite population from which the arrivals happen to the particular queuing system, which is what we want to study. Wherever that is finite source, we will mention that as well. So, otherwise we will assume that this is the case, and we will be mainly concerned with the steady state or equilibrium analysis of such a queuing systems, though as a point of departure and to make you aware about the other side of the analysis, which is the transient analysis, we will consider one simple model. Okay. Otherwise, mainly for all throughout the courses, like we will be concerning only with steady state or equilibrium analysis, because that is probably sufficient to answer many of the questions that you want to answer with respect to the particular queuing system that you are trying to consider or analyze. Okay. And this model, as we already said, is also referred to as exponential model because of its obvious relationship with exponential distribution. Now, again we will come back to birth death process repeatedly because this is the last time that we will be doing. After that, we are not going to come back it again, right. So, a BDP is a CTMC on the state space set of all non-negative integers with states transition occurring as unit jumps up or down from the current state. So, when n is greater than or equal to 0 and the time until the next arrival, which is what regarded as birth, follows exponential distribution with parameter lambda n. So, at arrival what happens? The system state moves from n to n plus 1 and will be at the rate lambda n. Now, whenever n is greater than or equal to 1, so there is at least 1 in the system, the time until the next departure is basically regarded as a death would follow exponential with parameter mu1. So, that means at departure the system state moves from n to n minus 1 at the rate mu n. So, here the states we mean the number of customers in the system or simply number in the system. As earlier, like if we draw the state transition diagram, right. So, the 0 is one state, 1 is another state, 2, 3, these are all states. The arrow and the quantities that are written above or below these arrows would depict the rate at which this moves from one state to the other. So, from 0 to 1 it moves at the rate lambda naught, from 1 to 0 it moves at the rate mu 1. So, and hence you will have this as the behavior. So, once you understand the system, then basically you need to figure out what would be the transition that might happen here. Okay, generator matrix for this BDP is this Q, which is what is given here. Now, you can see the holding times in particular state, right. We said this what this diagonal entries, the negative of that will give you the parameter for the exponential holding time in a particular state, because this is a CTMC that we are considering here. Now, here you see, for example, here it is lambda naught, which means this will be once you start the system, suppose if it is 0 is what you are observing at point of time, then it will remain at 0 for an exponential amount of time with parameter lambda naught. Okay. At state 1, so before it makes transition to the next state 1. Now, suppose if you are in state 2, right. Now, how long it will be here? It can go out of state 2 in two ways. One is this by a birth or a death, right. So, the time up to which this system will stay in this particular state will be minimum of these two, right. This is one is exponential with parameter lambda 2, the other is exponential with parameter mu 2, right. So, the minimum of these two exponential will be again exponential with parameter lambda 2 plus mu 2, and that is precisely what you are observing it here, right. So, the diagonal entries, the negative of the diagonal entries will give you the parameter of the corresponding exponential distribution for the holding time in that particular state for a BDP, right. That is what you will see here. And this is of course moving to state 3 and so on, that is what you get here. So, this is the holding time distributions parameter is what then you will obtain it here as well, right. So, generator matrix is this. If you denote Pn to be the long term fraction of time the system is in state n, or the limiting probability of finding the process in that particular state for a long time from now, then this Pn can be determined from, because we know that already this is all irreducible with appropriate conditions on lambda n's and mu n's. If they are assumed to be strictly positive, then this is irreducible, right. And you will see only that Pn can be determined from this stationary equations. Now, we consider this, this vector can be written in the component form, in this form, which will be then basically the difference equation is what then you will be obtaining it, or equivalently you can edit in this form as a flow balance equation, which we have already seen. This is the rate of flow out of state n, and this is the rate of flow into state n, and at equilibrium in steady state these two flows must be equal, and hence this equality is true, and hence this is called the global balance equations or simply balance equation. We may not use the word global often, but balance equation we always mean the global balance equation, which is what is given here. Now, how do you write down this is again you can look at this graph. For example, for 2, right, it is lambda 2 plus mu 2 times P2 equals lambda 1 P1 plus mu 3 P3 is what then you will get here, right. That is what is the equation that you will get here. To understand the corresponding Markov model, how you can write the flow balance equation from this state transition diagram, or if you have the matrix Q, of course, then it is PQ. So, this matrix is it's all equivalent representations, right. Whether you depict it through this or you depict it through this, it is one and the same to write down the flow balance equation for us to start the analysis, right. Now, one method which we call as iterative method of solving this is take this particular equation, you can write mu p1 equal to lambda naught p naught or p1 equal to lambda naught p naught by mu 1, so lambda naught mu 1 times p0, and similarly pn plus 1 you can write it in this form. From this we can now write down what is p2 from this quantity. P2 for n is equal to 1, if I write it, I will get P2 which is lambda plus mu 1 plus mu 2 times P1 minus lambda naught mu 2 by P naught. Now, P1 I already know as lambda naught by mu 1 times P naught. So, I substitute it here and this term will get cancelled, right. This lambda naught mu 2, like when P1, when I put it as lambda naught by mu 1, then this mu 1 and this mu 1 will get cancelled, then one term will get cancelled with this. I will be left with lambda 1 lambda naught by mu 2 mu 1 times P naught, which is what is you get here. This is by putting the value of P1, simply simplifying. Similarly, P3, I know what is P2 and P1. If I substitute here, what I will be ending up with exactly this form. So, in general, one can show by mathematical induction that by Pn would be equal to this, or which in a compact form P naught times the product of lambda I minus 1 by mu I. So, this is the main equation that you can think, right. So, this is the main equation that you can think of as if you arrived at here. Now, here this is Pn, everything you are expressing in terms of P naught and as a product in terms of this lambdas and mu's, and that is what you are getting it here. One can show mathematically by mathematics because P1 is true, we have seen, P2 equal to, we have seen, you assume it for n and show it that this is true for n plus 1, exactly like something similar to this what then you will be arriving at. Okay. So, that is you have. Now, all Pn's you have expressed in terms of P naught, right. Now, since the probabilities must sum to 1, it follows that now P naught would be given by this expression, right, because I have to sum, this is all Pn, so I will have a sum, P naught will be there which is equal to 1, so that would give me this expression. Now, we observe that this quantity P naught is greater than 0 if and only if this expression, that is the expression which is there inside this bracket, this expression, this or mainly this series will be convergent. And this is what we defined it as the quantity S1 when we gave when this MBDP is positive recurrent or null recurrent business. And this is the necessary and sufficient condition for the existence of steady state distribution, because this is the condition that makes the underlying BDP as positive recurrent, and in such case it is already irreducible positive recurrent, and hence there is a unique steady state distribution which is also same as the elliptic distribution, which is given by the stationary equation PQ equal to 0 and summation Pn equal to 1. Now, like to satisfy this you need that this series be convergent, okay, and that is the necessary and sufficient condition for the existence of steady state solution. That so, this product solution obtained above is a principal equation for birth death queues and is extremely useful in analyzing a variety of queuing models. Once you know the rate, because here we remember we are given in terms of generically lambda n's and mu n's. So, now once you know the rates, then you can obtain the solution very nicely by simply putting it here, by simply Pn's is in terms of this. So, this is the main equation for the birth death in the iterative method. This is what the iterative method, this is the main equation, and once I know Pn's expressed in terms of P naught, then this is also gets simplified. So, this series, and under the condition whatever be the condition under which this series is convergent, that is the condition for the positive recurrence of the chain, and hence one can directly use. So, P naught is this and this, right. So, one can directly use. So, that is why this is a kind of a principal equation for a birth death queues, because once you have birth death queues you can simply substitute. That is going to be one of the way to solve. Now, you do not need to write down the this kind of flow balance equation and start from this to get solved. Okay. Once you know that it is a birth death queuing systems, simply determine the rates lambda n's and mu n's, substitute it in this to get Pn in terms of P naught, and the exact same thing will give you what would be this quantity P naught. Once we get P naught, then all Pn's are determined and you are done with the solution. That is how things will go, and that is why this will be the principal equation for birth death queues in analyzing the variety of queuing models which can be modeled through a birth death process. Okay. There is a second method of obtaining the same product solution is through what we call local balance equation. So, what is the local balance equation? That local balance equation is simply this. Okay. Now, look at this particular equation here. Look at this particular equation here. Lambda naught P naught is mu 1 P 1, right. Now, take the first equation with n equals 1. Now, what will happen then? On the left side, you have lambda 1 mu 1 times P 1, lambda naught P naught plus mu 2 P 2 is what then you will get, right. On the left side also there is mu 1 P 1 and this side is, let us say, lambda naught P naught, and from this equation we know that these two quantities are equal. So, this gets cancelled and you are left with lambda 1 P 1 which is equal to mu 2 P 2, right. Lambda 1 naught P naught equal to mu 1 P 1, lambda 1 P 1 is equal to mu 2 P 2. Now, one more step you go, you will get lambda 2 P 2 equal to mu 3 P 3 and so on, right. So, basically from this you will get that equation which is what we call as local balance equation, and that is what this equation is true, right. This is what you are seeing it here. Now, from here you can easily see Pn is equal to lambda by lambda n minus 1 by mu n times Pn minus 1, and you iterate it, what you will get is this expression, right. That is what you are going to get it. And this is what we call local balance equation. Now, what is this local balance equation, right? Remember this global balance equation we wrote with respect to state, right? Looking at the state and when, what is the flow into the particular state and out of the particular state will give you the global balance equation or simply balance equation. Now, this one you can think as if you are standing somewhere in the middle between this n and n plus 1, and you are looking at the flow across like this side and this side. So, this side flow is given by lambda, so for example here if you are looking at it, okay, this side flow is lambda n minus 1 P n minus 1 and this side flow is mu n P n, and for equilibrium to exist these flows must be equal and hence you get this equation. So, this is one can write down local balance equations directly also for birth death queuing models, but this is not true for any general Markov chain. Okay. Global balance will always imply local balance, but this local balance need not always imply the global balance, and there is another concept called reversibility, and if chain is reversible, of course this both are one implies each other, but in this case we do not need to worry, because we will always, that is why we always handle with the global balance equations or simply balance equations or flow balance equations. But for birth death there is a simpler way of obtaining the flow balance which is via this local balance, and that is as you are looking at as if you are standing somewhere in the middle, not on the state but somewhere between two states, and you are looking at the flow on the one side and the flow in the other side, and in equilibrium since they must be equal, that gives you the local balance equation. This is only like as an additional information we are giving, but we will not use this local balance in any of our analysis. We will always write global balance equations, right. Now, consider having understood BDP again once more with little bit more details. So, we will now consider the basic model which is called as MM1 queues. Okay. So, this is the simplest non-trivial and interesting queuing systems, because randomness you have brought in. If it is deterministic, then of course then suppose if in our notation what we mean, this M denotes the inter-arrival times, the second M denotes the service time and one server with infinite capacity and FCFS discipline, right. Now suppose if these are all deterministic, then there is nothing much to analyze, everything will fall through, right. But the moment you bring in randomness, the simplest model is basically this MM1 model. So this MM1 is in Kendall's notation, we just explained what does that mean. Now the study of this behavior of this MM1 system is very fundamental and vital on many counts, because this serves as a benchmark for any new methods that you develop or any new performance measures that you may develop. Right. So, first of all, anything you develop and you try to apply for an MM1 queuing system to see that things work well, or what improvements it gives, or whatever is the case that you are looking for it. Okay. So, this in some sense is a benchmark model, because anything that you want to do, you always try to do at the level of MM1 queue before you move to the any other queue, say MG1 or anything of that sort. Okay. And another thing is, many of the behavior, the quality nature of this behavior that you observe in MM1 is what you would see across more complex queuing systems. Okay, so the behavior that you observe here is what would be similar to what you would get to observe in more complex systems. Okay, so the major aspects of any complex queuing systems can be heard if you analyze the MM1 version of it, okay, MM1 type. Okay. So that is why the understanding of this MM1 queue is important. It is very simple, it is not at all complex, but you have to look at in a way whether what is that it is giving you, what is that you want to take out of the analysis of this. So you always have to look for it to get what is the nature of this behavior and so on. Okay. So that is why the study of this simplest model is what is very important. Now what is an MM1 queue? It's a single server queue with a Poisson arrival process and with an exponentially distributed service time distribution. So inter-arrival times are IID exponential lambda and service times are assumed to be IID exponential with parameter mu, and they are independent of each other, which there is no relationship between the arrivals process and the service process. These rates lambda is greater than 0 and mu is strictly greater than 0, they are all fixed constants. As per the 4th and 5th notations in the Kendall's notation, it is assumed that there is an infinite waiting space is provided and that the customers are served according to the first come first served or first in first out discipline. So, in pictorially, like if you want to depict this particular queuing system, what you will have? You will have a Poisson process arrival with rate lambda. So, many a time it simply the rate lambda would be mentioned here, that is all. So, that always means Poisson process arrivals. There is a waiting space where people queue and the space, the limit or the space here is infinite, and there is a single server who works at the rate mu, and once the customer got served, it departs from the system. So, this part is what typically like you would see as a typical pictorial representation of such a queue. So, there is a lambda here, there is infinite waiting space, single server with rate mu and then gets departed. So, this is what you would see here. Now, the quantity of interest here is n of t, number in the system at time t. Now, this process n of t is a birth death process. It can be modeled through a birth death process with rate lambda n equal to lambda for all n greater than or equal to 0 and mu n equal to mu for all n greater than or equal to 1. So, the transition rate diagram for the BDP, the corresponding BDP are for the MM1 queue. Now, we will simply start saying that the transition rate diagram for an MM1 queue, meaning the transition rate diagram for the number in the system process, how it behaves, right, is basically 0, 1, 2, 3 and so on as the states, which gives you now number in the system, the number of customers in the system in equilibrium. with or in other ways in the system basically, right. So, this is with the rate lambda there is an arrival happens, a customer arrival happens, and with rate mu there is a customer departure happens, right. Now, you can also look at what is the Q matrix here in this particular case, right. So, you can always look at here, this is minus lambda, lambda 0, all these things, this is mu minus lambda minus mu, lambda 0 and so on, 0 mu minus lambda minus mu, and this is lambda and 0 and so on. So, this is the Q matrix that you will write it for this particular MM1 Q. Again you see the tridiagonal structure except this portion except the first row, the remaining rows are all in a way identical. So, that gives you, this kind of equations very nicely. Now, the quantity of interest here whenever we have such a system. So, now you assume that things are inter-arrival. So, this basically the conditions that we have put for this MM1Q, that in a small interval of length say delta t, what is the probability of an arrival, what is the probability of a departure, what is the probability of more than one event happens. That is how you typically define for a BDP, and exactly same thing is happening here for MM1Q, right, because of your assumption that the inter-arrival times are exponential, service times are exponential. So, basically you are getting exactly the same condition, and hence this can be modeled through a birth-death process because the transition happens one at a time. So, the quantity of interest here will be for this queuing system is the number in the system at time t, if the probability that it is equal to n is what is this Pn of t. So, this is what our original system P dash is equal to P times Q, right. So, you know that this P dash of t, this vector is PTQ is what then is the system of equations that which is forward Kolmogorov equations. Now, for this particular Q, what you will end up with, if I write this P naught is a vector, this P is a vector and Q is the matrix that is given here. So, you will get this as the system state probabilities for this equation is fundamental for the analysis of MM1Q if you want to see. So, ideally what we want, we would seek a solution to this system of equations so that at any point of time t, we know what is the probability that there is n customer in the system, right, which is what is this solution is what is called as a time dependent or transient solution, because we want to look at Pn of t subject to the initial distribution whatever you are assuming Pn of 0 equal to 1. This is a probability distribution, which means the sum of this Pn of 0 must be equal to 1. And if it starts at 0, so then simply P00 is 1 and the rest of all Pn zeros are all 0, whatever is the distribution is what the initial probability distribution. Subject to this, then we would obtain solution to this is what ideally we would like to have. If we can have that, then we can have even in time dependent nature where the system is not it reached the equilibrium level. So, it is in transient phase, even then you can answer any question, right. But for now, we will come back to this solution to this particular system of equations alone, which means for MM1Q alone, the transient solution we will come little later. Okay. But for now, we will focus on the equilibrium behavior, which means that we assume that the system has reached an equilibrium, then system is in a stable situation, system has reached a steady state situation. So, it is operating under a steady state situation, and that situation we want to look at what are these quantities. So, that means we are trying to determine this Pn, which is basically limit t to infinity of Pn of t directly rather than obtaining Pn of t and then taking its limit, right. We have seen we said that complexity is there, but we will see how complex is that as an example for MM1Q little later. But in all our analysis except that part when we are going to the transient analysis, the rest of the complete course we are dealing with only equilibrium analysis, right. So, we are always interested in what happens to this Pn and how we can get this Pn, which is what is of our interest. So, where we are now, that we are assuming that the MM1 system is in steady state now. Okay. So, flow balance equations, we will not even anymore call global the word, we may drop, but we simply say balance equations. The balance equation for this system, as we know already, is what is this, or equivalently we can write it in this form, right. And we will at least exhibit 3 methods, not that these are the only 3 methods, there are many more methods, but at least 3 of the methods that we will try to exhibit to solve this system of equations, to get the solution for this Pn, which is not a very complex one, it is very simple. Okay. So, the one is iterative method, which we already exhibited little earlier, and the generating function method and the operator method. The purpose here is that it is not that one is difficult or the other. In MM1 case, all 3 are equally easy, there is no problem at all. But the more complex queuing systems that you are going to consider, it may turn out that one method may be little easier to analyze that particular system than the other method, right. You will try to get. So, you will try to adapt which method is going to work. That is why I said these are the not just all the methods, there are many more different methods can be utilized, right. But we will highlight these 3 methods for the time being, because these are the things which we will be using it in the future. Okay. The reason is just for illustration purpose how this method works, because later on we will simply employ this method and then we will simply say analyze the models, right. But then again you can look back here at this point of time, like how exactly this method works here. Okay. So, the first one is iterative method. As we said that already, this is a birth death process with this constant rates of birth and constant rate for death. So, we can directly apply the iterative method given earlier for the BDP with this parameter. So, what was that? Recall Pn was given as P naught times, in terms of P naught it was expressed, right, product of lambda I minus 1 by mu I. Since all of these are constant, so this has become a constant. So, this is basically to the power n, right. So, P naught lambda by mu to the power n is what your Pn's are. Now, substitute this into this total probability condition, right. That means this, now Pn is already we know is equal to this, which means this, where this rho, which is what lambda by mu is, as far as MM1 is concerned, this is also equal to R, because R is what lambda by mu is, since there is a single server here which is also equal to rho, and hence this is offered load, because R is what is the offered load. Traffic intensity means this rho. So, in this particular case for MM1, this one and the same, this is the offered load or traffic intensity. It may not be true in general for both of them are equal, rho need not be equal to R for all systems. When you have multi server, of course, this is not equal, but in this single server system this is equal to. So, it is interchangeably you can call the offer load means to the system only you are looking at it. Traffic intensity is basically per server you are looking at it. Here since there is a single server, so it is one and the same, it turns out. So, this is what is rho, and P naught summation rho to the power n is what equal to 1. Now, from this we can get this P naught to be this, which is equal to 1 minus rho, provided rho is less than 1. This is for using your geometric series, right. What is the geometric series expansion for this 1 by 1 minus rho is exactly equal to this for rho less than 1, right. So, using that we get P naught equal to 1 minus rho. So, if I substitute P naught equal to 1 minus rho here, so this is 1 minus rho times rho to the power n is what I would get as the solution, which is again you see as geometric distributed random variable like Pn, which is probability of n equals n. So, this n we said that it is limit t to infinity of n of t, in the sense that it is a distribution sense, right. So, Pn is equal to probability of n equals n, which is equal to this distribution for rho less than 1 is what you will get using this iterative method, right. That is what we are seeing it here, right. This is we are simply whatever iterative method that we have already developed there, we are simply employing it with this constant parameters and we are getting the solution Pn, right. This is one method. The other method is using generating functions. How do we do? Now, we define a generating function p of z for this pn's by this expression. We know z is complex and with mod z less than or equal to 1 and this series converges, right. So, what we do is that we somehow try to obtain this p of z and express this p of z as a power series in this form, so that I can, as a coefficient of z to the power 1, if I look at it, what I am going to get is this pn's, right. That is what we would like to do in this particular case. This is the approach, right. This is typical approach. This is what you try to do later on also for more complex queuing systems. So, that is what we understand. So, what you do is, where do you start? You start with the flow balance equation. The flow balance equation, we already said that this one, P1 mu P1 equal to lambda P naught. So, lambda by mu divided by mu. So, the lambda by mu is rho. So, P1 is equal to rho times P naught. Pn plus 1, again mu Pn plus 1 equal to lambda plus mu Pn minus lambda times Pn minus 1, right, if you rewrite it slightly, and again divide by mu. So, you will get Pn plus 1 equal to 1 plus rho times Pn minus rho times Pn minus 1. So, we are writing it in this form, so that n plus 1, you are writing it in terms of n and n minus 1 for our convenience, right. Whereas, in the balance equation, n was in one side, n minus 1 and n plus 1 was in the other side. So, we are just slightly rearranging and we are rewriting in this form. That is all you are seeing. This is exactly same equation as earlier. Say for example, where you have written this here, right. This is exactly same equation. You divide by mu and write it P1 equal to rho and Pn plus 1 in terms of Pn and Pn minus 1. This is what you have here, right. Now, what you do, take this second equation here, okay, multiply this by z to the power n and sum this is what you are going to do here, right. So, by that what you are getting is essentially this Pn plus 1, you multiply by z to the power n and you are summing up is what the left side. Here it is Pn z to the power n and its sum minus rho times this what you get here. Now, what you do here, you multiply and divide by an z, right. So, 1 by z will be outside and this quantity will be Pn plus 1 z to the power n plus 1, which from this if I look at it, it starts from 1. So, basically from the term from P2 onwards it is there inside this sum. So, it will be equal to then P of z minus this first two terms which is not there inside this sum, which is minus P1 z minus P naught rho m plus 1. Here it is 1 to infinity. So, the first term is not there. So, P of z minus P naught. Here it starts at 0. So, it is you take 1 z outside to make this z to the power n minus 1. So, that will give you this expression, right. You are just obtaining this using this. You multiply from this, you are obtaining this equation and from this equation. Now, what you do, you already know from this first equation P1 is rho times P naught, okay. So, P1 is rho times P naught you know. So, you substitute that here and you will get this expression, and from this P of z you club at one side and the other terms you are putting on the other side, right, of the equation. So, you obtain it as, you can solve this after writing couple of steps, P of z as P naught times 1 minus rho z. So, P of z you have not completely determined, you have obtained in terms of this P naught. Now, this P naught needs to be determined from the condition, initial condition, from the condition. Condition is what? Suppose if I look at P of 1, if I look at it, what is my P of 1? P of 1 is summation Pn 1 to the power n, which is simply 1. So, summation Pn which is equal to 1, right. So, P of 1 is equal to 1. So, therefore, in this particular case, if I consider P of 1, this will be P naught by 1 minus rho, right. P naught by 1 minus rho, this must be equal to 1. That gives me my P naught is 1 minus rho, right. Now, since Pn is probability distribution and hence this is non-negative, whenever z is real and z is positive, this p of z also will be strictly positive, right. Therefore, my p of 1 will be strictly greater than 0, and this implies that this p of 1 which I obtained as p naught by 1 minus rho must be greater than 0, and if this must be greater than 0, that must mean that rho must be less than 1. Okay. So, in summary, my p of z would be p naught, which we will obtain to be 1 minus rho. So, 1 minus rho by 1 minus rho z for rho less than 1 and mod z less than or equal to 1 is what I would obtain it as p of z. Now, I have completely determined the p of z, which is the generating function of for this particular sequence for this particular quantities pn's, okay, which again using geometric series I can write this 1 by 1 minus rho z as summation of rho to the power n z to the power n multiplied by this term constant, which is 1 minus rho outside here. Now, by looking at the coefficient of z to the power n from this power series, we get Pn to be this as earlier, right. Like earlier case, we also obtained Pn. So, how did we do is what is important here, not just the calculations are not complex. We consider the flow balance equations, we defined the PGF, and from this flow balance equation you to try to determine what is this PGF explicitly. Now, in that process you will use the boundary conditions that you will get for this PGF to determine this PGF in a nice complete form, okay, which is 1 minus rho times 1 minus divided by 1 minus rho z for rho less than 1 mod z less than 1, which now if I can express as a power series, I can extract the coefficient of z to the power n to get the corresponding probabilities. That is what precisely we did here. This is the approach, and this is what you will need to remember if you are using it elsewhere too. Okay. So, this is the PGF approach or the generating function approach. Some observations based upon this algebraic form of this for this model can be given, which is maybe is relevant. I mean, it is very simple here, but the similar idea is what is going to be prevalent elsewhere when you are having more complex situation. Look at this expression, this is a rational function, right, meaning that it is a quotient of two polynomials. This is a constant polynomial and this is a linear function of z, right. So, the numerator is a constant, denominator is linear. So, and this denominator has a single 0 1 by rho, which is the reciprocal of this traffic intensity, and its value is greater than 1. So, we will be looking for a root of that nature if we have multiple roots, and if the polynomial here is not linear, but quadratic or of order anything, then you look for as rows which are of having this property, the 0 of denominators which value is greater than 1 is what then will give you the required quantities. Okay. So, this is a rational function. The rational function is what is easier, whether it is Laplace transform or generating for z transform. The rational functions are easier to deal with it, because then you can make partial fraction expansions for these rational functions, and you can write down nicely, and you can try to get the corresponding series expansion, so that you can get the quantities there. That's a nicer form that you would expect to have. Now, for some models, not here, it may be easy to find the expression for P of z. Okay, you may able to arrive at up to this part. For some models, even this may be little difficult, but for some models you may be able to arrive at an expression of this form. You can be able to arrive at the expression for P of z, but again it may not be possible to express this as series expansion as a power series, so that you can obtain as a coefficient of z to the power n the corresponding probabilities. So, that may be difficult, but still whether it is in the any stage it is there, the information that the P of z has is still useful. Okay, still it provides useful information. Say for example, if you want the mean number, which you can obtain it expectation of n, which is given by this, which you can differentiate this PGF and evaluate at z equal to 1 to get this p dash of 1. You will see later on when we deal with a little bit more complex models, like at whatever stages we will be using this kind of ideas, right. So, the L can be obtained from here, even though you do not have explicitly what is this Pn. So, from P I can differentiate with respect to Z, and I can obtain its mean number in the system. So, this is some observation that you are making with respect to PGFs, that ideally, like the algebraic form rational functions is what we want, and that will give us the ideas of how one can handle this PGFs and how we will get this zeros for the denominator, for it will serve our purpose. And even if you are not able to obtain explicit expression or not able to get from the PGF the PNs, you can still obtain some useful information. So, this is the second method that we have using it. The third method is using operators. This is much similar to the differential equation that you might be aware, because that is also an operator. This is a differential operator. This is a generic operator, which is what the difference operator basically you can say here. Okay. So, recall that this is our set of equations. So, where we have Pn plus 1 is given in terms of Pn and Pn minus 1. So, this is what we call linear difference equations, and we want to solve such linear difference equations. So, to do that, let us look at a generic approach how one can do. So, we define a linear operator which we call it D on this sequence by this. So, D acting on An will produce An plus 1. Then D acting m times on this An will produce An plus m, right. This is the operator that we have here. So, if you use this operator in a general linear difference equation with the constant coefficient, suppose if I have this Cn plus 1 and so on, Cn plus k, they are all constants, An plus 1, An plus k is what the sequence An is what I want to determine, and that satisfies this linear difference equation. Then if I use this operator I can write everything in terms of this, where Cn plus 1, this An plus 1 I can write Dan, and similarly An plus k I can write D operator at k times An. Okay. Now, this from this you can try to see how to solve. We will take a simpler case of a second order case. So, what do we have second order? We have this as the second order linear difference equations, right, which can be written in this form if in terms of this operator. So, the corresponding characteristic equation is basically this must be equal to 0, that is C2 some r square plus C1 r plus C naught equal to 0. Now, the roots of this equation determine the form of the solutions for An, right. What you do in differential equation in a linear second order differential equation is exactly the same, right. Now, suppose R1 and R2 are two distinct real roots. If not, what is the case? Like exactly same as the differential equation whatever you do. But here suppose assume that if R1 and R2 are two distinct real roots of the characteristic equation, then we know R1 to the power n is a solution to this difference equations, and any constant times of that would also be a solution to that, and similarly D2 the constant times R2 to the power n is also a solution to them. They all this particular quantity as well as this particular quantity, both of them are solution to the second order linear difference equation, which is equal to this. You can simply substitute for An d1 r1 to the power n in this equation, and you see that this equation is satisfied exactly, because r1 is a root of this. Similarly, this. So, the general solution, the most general solution is d1 r1 to the power n plus d2 r to the power n is what is the most general solution. So, this is the theory is similar to solving linear differential equations, right. That is what you observe here. Now, this idea, this is what is the difference equations and how one can solve. Now, what is for our model? For our model, the equation is mu times p n plus 2 minus lambda plus mu times p n plus 1 plus lambda times p n equals to 0 is what is our equation. This is what the flow balance equation gives you, right. So, the Pn's then are solution to, if I do this operator, apply the operator here. So, this is d square times Pn, this is dPn and this is simply Pn. So, I will get this times Pn equal to 0, and what are the boundary conditions? The boundary condition P1 equal to rho P naught and summation Pn equal to 1, right. Now, what is the characteristic equation? The characteristic equation in this particular case mu r square minus lambda plus mu times r plus lambda equal to 0, and this gives two roots. The roots are 1 and lambda by mu, which is rho here, okay. And hence the general solution for this is some constant times 1 to the power n plus some other constant times rho to the power n is what is the general solution. Now, we have two boundary conditions which we have to use to determine this d1 and d2. If you do not have, then this is a general solution that you will leave. Suppose if your boundary conditions are there here to determine what is this d1 and d2. Now, we know the summation p1 must be summing to 1. Now, this d1 is a constant, and for this to be finite, we must have d1 equal to 0. Otherwise, what will happen? Suppose if you sum here, so this quantity becomes infinity, right. So, in order that is not happening, this sum must be equal to 1, my d1 must be equal to 0. So, I plug it d1 equal to 0. So, Pn will be d2 times rho n is what then I have to get. Now, I still have to determine what is d2. You look at the other boundary condition, which is P1 is rho times P naught. Now, from this P1 is d2 times rho, right. P1 equal to, this is the boundary condition, this implies this because P1 is also equal to d2 times rho from this expression. So, d2 must be equal to P naught, and hence Pn is now P naught rho to the power n, and P naught then can be found from 1 minus as 1 minus rho from the total probability condition that we have here. So, giving us the same expression as this, okay. So, this is 1 minus rho and rho to the power n is what then you will get finally here, right. This is the same result that we have. So, these are three different methods of solving this particular MM1 system, right. Some observations before we go further. This is geometric distribution, and Pn depends on lambda and mu only through its ratio, which is rho, not individually on lambda mu. What is the lambda and mu? These are the parameters for this model, but the steady state distribution depends only on its ratio. So, whether it is lambda is 2 and mu is 4 or lambda is 4 and mu is 8, it has the same behavior. So, it is only rho that matters here, okay. One thing that you observe. Second thing is this is the condition that rho less than 1 is equivalent to saying that lambda less than mu, which means the arrival rate is less than the service rate, right. I mean, number of customers who arrive and number of customers who get served must satisfy this intuitive, or equivalently if you write the service time for a particular customer, average service time is what 1 by mu, because this is exponential. This is 1 by lambda because this is the intra-arrival time, this is the average intra-arrival time. So, the average service time must be less than or equal to the average intra-arrival time, right. So, this is the condition which is also makes an intuitive sense, but why there is no equilibrium solution when lambda equal to mu? You can see that when lambda equal to mu also exactly it would match, but exactly it would match provided there is no randomness here. Because of this randomness, there may be patches at which the system will be empty, and that will not be able to serve because the mean service rate is exactly equal to the mean arrival rate. So, it will not be able to serve completely, and then Q will start building up, so that the stability is lost. So, this is the condition for the ergodicity of the BDP and the stability condition for MM1. When we talk about queuing systems, we will say what is stability condition. And this distribution, this allows to calculate various equilibrium performance measures of the system, which we will see in the following lecture. Okay. So, we will stop here at this point after having obtained the equilibrium system size distributions for an MM1 queue. We will continue with performance measures in the next lecture. Thank you. Bye.